data stream processing. Can we finally forget the batches? Very quickly about me. So my name is Dominik Wagenknecht. I'm a senior TechArch out of the Accenture office in Vienna, Austria. We also have very nice weather, but better temperature. And for about 10 years, I've been dealing with data in all kinds of industries. So that's probably why I'm always chosen for the data topic. So, batches. Why do we do batches? Batches we primarily do out of two reasons. The first one being data needs to move. And I will point out why. And there's actually this second reason that sometimes you want to process something within a batch. But that is getting considerably less and less and less, and we will see why. So we need to move data. Why? Because we need to get the data where it's actually needed. We are kind of in this transformation from those single-purpose systems, and Thomas Nyström always points out the big black box, which is the monolith. So I essentially took that and painted a big black box in there, which then below it has this gargantuan database where everything is joined. And it's interesting, that kind of stuff still exists. I know a kind of startup out of Germany. They revolutionized somehow the market to find the right consumer loan and the right mortgages and stuff like that. And they started like 10 years ago. And it was all technical people. So those technical people, they had no clue about CRM systems, about personnel systems, about a system where you could track your vacation or something like that. So they built everything in the one system. So you have this one system that not only does the core reason the company exists, namely finding the perfect deal for a loan. It also has the vacation of the employees. It also has the financial planning of the company, and it has all that stuff inside, which is pretty nice actually, because they can just join everything together. Yeah, it's really easy. But of course, the world is moving forward, so we are going more towards separate services. We are going more towards separate databases, and that's not only because we believe that microservices are the right way to go. That's also because we are specializing. Yeah, so in the past, if you look at CRM, yeah, you couldn't really call it CRM. Yeah, for example, in banks, often you just had this master table with the clients, and then you added a few columns. Yes, I spoke to the customer, and so on and so forth. Nowadays, a customer relation management system is really an intriguingly complex thing. Yeah, often you use systems like Salesforce, you use systems like MS Dynamics. Just recently for an insurance company, we put a full graph database in place for the customer relationships management. Because it's actually important that you know who the customer is and with whom he's related, so that to the related people you give the right advice and the right customer service and so on and so forth. In private banking, there are those nice examples that there's essentially this rich guy who has an extended family, and although the extended family doesn't have a lot of discipline when it comes to money, you still need to treat them like private banking customers. So stuff like that is suddenly becoming complicated. So we are splitting up the systems out of a lot of reasons. Because the world is getting more complex, because we want higher agility, because we need the data where it's needed. But at the same time, now we have all those systems. We have those microservices out there. We have all those software as a service systems that we bought, that we got in. We have this melange essentially of core systems, microservices, connected systems from HR to something else. And then analytics came across. And reporting was always there, and artificial intelligence is coming, and guess what? You have to do that somewhere where the data is. If you followed the introduction talk, then essentially artificial intelligence and all the analytics stuff beforehand, it all lives on the data. So you again have to bring it from A to B. So essentially, we need to integrate services. We need to integrate a lot. So Let's do batch, shall we? Oldie but goldie. So how do we do batch? This is more or less a picture of this classic ETL style batch processing. I guess most of you have something like that, right? And why do we do that? Because we need to get the data from A to B, because we need to do something in a batch, because we need to process something at a certain rhythm. And it's easy. It often starts with a simple innocent script that executes a select over here, writes something into a CSV file, processes along, and loads it into a target. And this of course then advanced, because it's a pretty efficient thing. You take the off hours when your system is not heavily under load, or at least traditionally it wasn't under heavy load. Nowadays with mobile apps everywhere, the usage patterns are changing, but in the past, your branch closed, system load went down, batch window started, systems went more or less offline. You have all those nice ETL software packages in there, so the Informaticas, or in newer times more something like Talent and so on, that do that. And it's efficient. You pay a relatively high overhead to launch it off, yeah, because you really start your own process. Maybe you have even a scheduler like UC4 in place so that you have the oversight of all that. So you start a very heavy process, you move a lot of data, you dump it, you process, you load it. And it's a successful model. And it has also been revolutionized within open source with stuff like the MapReduce framework. And for example, Apache Spark is like batch processing on steroids. You can really do everything on Spark for this kind of processing. But they do it for analytical purposes, and there you need it, because you need all the data to do the clustering, to do all that kind of stuff. But you don't necessarily for this simple. So we have a very high initialization effort, but this initialization effort of unloading, loading, doing all the transformations is totally compensated by the efficiency, because we do 1 million records at a time or something like that. That's then in the end efficient to do this bulk of data. But of course, this is nightly, and we can now start to make it quicker. And I don't know, what's your lowest batch window time? Does anyone have an hour? That batches run hourly, half hourly? Anyone? Yes? 15 minutes? 5 minutes? 10. Okay, so 10 is the lowest. And 10 is already pretty advanced. Because of course, business wants that stuff quicker. I've spent a lot of time in banking, and initially in banking you got your files where you did the mass transfers. You got them somewhere in the wee hours of the morning, and you just started the one big batch process. But then everything became more real time. So we got it in the middle of the day, and so you went down to a quarter hour. Yeah, so from every hour to half hour to quarter hour. And quarter hour already people got very, very nervous, because it gets really, really funny once the unload of the next job overlaps with the unload of the previous job, or with the processing of the previous job, and you somehow need to put safeguards in place in your entire scheduling mechanism, because actually you never tested that stuff for working in parallel. Yeah, and then one batch is triggered too early, and everything kind of gets messed up. So the message here is really batch in this classic sense, yeah, and I'm making really a point here, is basically not enough, especially not for the business people. So it's basically always too late, yeah, because people don't want to wait a day, people don't want to wait half a day, people don't want to wait an hour, and then people don't want to wait 15 minutes. They will never be happy with that. And it also, in the past, it might have seemed elegant, because traffic goes down, we do our batches, then we open again, that the traffic patterns are changing. Yeah, flights are going through the entire night, users are surfing around all the time. Of course, it's a little bit less in the night, but it's not the old way. And the batch produces something pretty nasty. It really generates very bumpy load patterns. Again, in banks, we are typically quite afraid on the quarter end specifically, and then on the year end, that the batches for the quarter end get done before the Monday morning traffic starts. Because if they don't make it, it gets ugly. Yeah, because you start competing. So it's not really good. Yeah, you get those shock waves that go through the system in multiple waves until this entire thing is processed. Then they are mostly on the night. Yeah, that's possibly cool for operations people that love to work in the night and love the extra money they get in the night. But in general, especially the development people are not very happy if they call it in the middle of the night. So in general, it makes people quite unhappy, and it's pretty hard to test. So anyone tried to do automated batch testing? No? But you have automated unit testing and so on and so forth. So again, there you see, you can do a lot of automation nowadays in software. You can do your fancy continuous integration pipelines and do automated tests, but you cannot really do automated batch testing. I mean, you can, but it's a ton of effort and nearly no one does it. So that means that whenever you change something where a batch is involved, it gets nasty, because it means you have to wait, or you have to manually start the batch or do something to confirm, okay, the batch is still working. Of course, to all of that, exceptions apply. There are some things that are perfect on a batch, right? So that's things like interest rate calculations, because the law says we make that per day. Or it's something like monthly billing. Yeah, at some point you start a batch and you trigger the billings, but you can design it better. And here is a very, very blunt statement, and it's for sure not true in 100% of the cases, but in general, you cannot really go from batch to stream. You can try to go down with your time windows, and then you reach 10 minutes, which is already pretty good. You reach 10 minutes and you can't go faster. So how would this look in a stream? Because you could do that in a stream. With streaming, you would essentially go in and say, okay, we have the sources, and from the sources we get all the updates. If it's a database, that could be, I don't know, change data capture, or you have some trigger or something like that, and you get single pieces. Yeah? And then those single pieces go into the event processing, and you make single event processing, which is, by the way easier to test, because it's a single event. You throw it in, you can compare the new value to the old value and automatically see if it's right. I'm simplifying here. And then you can push the data towards the target, the resulting things. Now this picture, of course, now looks very, very easy. The truth is, very often within this big event processing, you need to do stuff like joining things, which is something that batches do very well because you have all the data, but which is quite a bit trickier in a streaming use case. But there are the streaming frameworks nowadays that can keep track of a certain state, and you can refill them. So there are nice solutions to essentially also handle state in between there. And the key difference between the streaming approach and the batch approach is, here the streaming is always running. So it's there and it's live. There is no scheduler that goes there every 15 minutes and launches something. It's hooked up there, it's hanging there, and you can observe the latency. Yeah? You can really observe the latency and look at it. And the interesting thing is, while from a batch in general you cannot go to a stream, it's quite easy to go from a stream to a batch. Because if you defined your processing on the single events, it's quite easy to batch them together and do them in multiples. Because many source systems are not necessarily capable of providing a stream, but maybe it's fine for business if the data is like only fetched every hour. Yeah, you add an additional column that has a change timestamp, and then you make a select on the change timestamp, and you just use the old methods and then push it into the stream. So while you cannot go from a general batch description with fancy joins into streams, you can easily go from streams into a batch operation for efficiency. And the entire thing works continuously. Now that's all very simple pictures and so on and so forth. So the question bears, why now? Yeah, we could have done that 10 years ago. We could have done that even earlier. Because message queues and other mechanisms to work on streams exist essentially forever. So I've done quite a bit of work on mainframes, and there's MQ, and it works. But it's a cost and efficiency thing. So whenever you draw up MQ, the mainframe guys and also the other guys get nervous, because it's like, how many messages are you going to send over this thing? And you're like, 5, 6, 7,000 per second. And they are like, whoa. Now it gets tricky. We need to size that. We don't know how that is with the sysplex. So then it gets funky. But again, open source really established a different game there. So there came LinkedIn and Netflix and friends, and they work massively message-based. They don't give you a new movie recommendation on a daily basis. They give you a new recommendation when you watch the movie and you said, yeah, 5 stars, I like that thing. Then they give you a new recommendation right there with a little bit of lag. Sometimes you can try and you hit F5 to reload, and you will see, now I have better suggestions, because they do it asynchronously. And the interesting thing is that for many, many things, you don't need the traditional guarantees of a classic message queue. So a classic message queue, I don't want to tell you here to abolish classic message queues. Don't do that. They have their use, but classic message queues have certain guarantees, and I will come to that on the next slide, that you don't need in this typical let's move data from A to B, let's process something, let's crunch a little bit of data use case. Yeah, you need it if you really do it in a processing way, like you do payments processing or something like that. But for other stuff, you just need a messaging store, and there came Kafka. The weird thing is, right now, there's not really an alternative out there to Kafka. I don't really know a commercial product that would be way better. There are a few other open source products that do something similar, like this distributed log that was published by Twitter and is now also an Apache project, but right now it's Kafka. And additionally to the messaging system, where we traditionally had a message queue like IBM MQ, ActiveMQ, RabbitMQ, what have you, and then you did the processing, for example, in a Java EE environment with JMS, and message-driven beans, we now have an ubiquity of high-performance distributed stream processing systems. And watch for the distributed. Those systems really can take your job and execute it on a cluster of machines in parallel and handle the stuff. And if one of the machines crashes, it will restart the job at another location, which is a pretty nasty thing in JMS if you ever tried that out. Because if it crashes, it has some state from some multi-phase commit hanging there on the local disk of the Java EE web server, and if the Java EE server doesn't come back up and cannot load its state back up, you have to wait or cancel some transactions on some databases or other stuff. So they took away those guarantees, and you can work without those guarantees, and I have some tips on the end around how to proceed with that. There are the frameworks for that. So what is a little bit the issue with the classic way to operate with messages? Classic messaging systems essentially work a little bit like an ACID-compliant relational database. You put something in, and then you do a few other operations, and then you commit. Yeah? But that means for this poor guy here in the middle that he has to track all this state that is essentially floating in the air, already have it in there, waiting until you come with the commit, and then it's in. And you have to track that for all the sources. But it gets way worse towards the target, because here, you as a target, essentially what you do on your Java EE web server is you say, okay, let's do 50 threads for this JMS thing. So now these 50 threads go to my pure MQ and say, give me a message, give me a message, give me a message, and it hands out the message. And then it has to do a lot, because it hands out the message, and then you start processing. And the pure MQ in the middle has to wait until you successfully commit or roll back that you have processed the message. And if you don't process the message within a certain time frame, it also has rules how to deal about that. If your TCP connection suddenly disappears because your server crashed, it also has rules about it. Yeah. So you have this re-availability after a certain timeout. Then you can configure: do we put it in the same queue or do we have a backout queue? Yeah. So you have then this backout queues possibly on rollback, however it's configured, and then comes even the fanciest thing, and you often again see that on mainframe integrations where you send a message in and then you expect an answer on another queue, and then you have a correlation ID. And you look for the correlation ID for the transaction that you sent in to get the response. Now, that means that poor guy here has to have a lookup for the correlation ID, which means he has to build up a complete secondary index. And because here in the middle you have to handle all that, it's really, really hard to scale that stuff. Yeah? At a very big German logistics company that was outside of the mainframe, we scaled IBM MQ up to 15,000 messages per second through one server, essentially, with classic failover. So that was not yet the clustered version, because the clustered version didn't behave so great, and that was a lot of effort. We had to fly in people, we had to get in experts to get that message volume, and it wasn't small messages, it was a huge XML mumbo jumbo inside of that to get that working. And the weirdest thing about it, in many cases, especially for batch, you don't need that, and what is also pretty nasty is you lose ordering. Because if you pick something out and you process it, and then the next one goes to the other one, and then the first one fails and goes back, you lost ordering. But often you want ordering, especially in the batch use cases you want ordering. So it's for really different use cases. And what came and what essentially changed the game is the simple idea of a log file. And here we call it distributed log. It's still a simple idea. It's the idea of a file. So it's really straightforward. So we have the source, and here I'm trying to essentially with the blue arrow that originally I had to left to right, I'm essentially showing the time. Yeah, so old time is up there, new time is here. So here's the fresh data, up there is the old data. And of course, if we push data in, then we always add here. So the file grows larger. Visually here it goes down, so to say. It just keeps on writing. And all we do is we write data in, and when we write data in, then the distributed log can tell us, well, your message is at index 5. Next message, index 6. Next message, index 7. So it's very easy to keep track of that, right? And it's really, really efficient. Even on an old disk drive with a spindle, you just keep writing forward. Yeah, you can write at full speed. And now the idea is you no longer keep track of who got which piece of data already and backout queues and la la la. You go for a different operation and also tell the target that it just starts reading at a certain index. Yeah, and you just start reading. So you write here, you read here. And if you're close by, then typically the stuff is in memory. So you essentially you just pipe it through. And the challenge now is, because my system no longer gives me this nice transaction where I can read, and commit, or write, and then commit and connect it, I somehow need to keep track of my position. I somehow need to know I'm reader, I don't know, data warehouse, or I'm reader finance processing, or whatever. I need to know my position where I am, so that if I crash and I restart, I can start where I was, right? Because otherwise I reprocess data, or I reprocess too much data. And so Kafka has APIs in there, and the consumer APIs help you with keeping track. So what's the consequence of going for this distributed log? The consequence is we lose the full transaction support, which in our use case, let's get data from A to B and process a little bit with it. Let's get stuff integrated between different cloud services. Not necessarily needed. We lose the lookups by correlation and ID and so on and so forth, which again, in this specific use case, not really needed. However, what we win is incredibly high throughput. Really incredibly high throughput, because essentially your throughput is what your disk drives can manage. There is no real there is no real limitation in that. And this distributed log here can actually be sharded. Yeah, I can have multiple distributed logs, and essentially based on a custom ID or some other correlation ID, I can just say, okay, distribute it like so. What I also gain is I no longer have this situation of overfilled queues. Because typically within a classic message queuing system, the performance deteriorates if your queue grows beyond a certain size, right? Because your indexes get too big and your lookups get inefficient and you no longer can keep your indexes in memory. And at that point latest, you run into problems. Here it's just a file. Yeah. So worst case, you read from the past. Best case, you still have the data in RAM because it was just recently written. So you don't have really overfilled queues. In Kafka, you essentially just say, keep 5 terabytes or keep a week, whatever happens first, and then throw it away. You get strict ordering per log file or petition, however you call it. If you don't use Kafka, if you use a service like AWS Kinesis Streams, which is similar in nature. I think there they don't call it partition data, there they call it the stream or the segment or whatever, I forgot it. But this strict ordering is pretty useful, because if you have one modification after the other from the source system, insert, insert, delete, update, insert, 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 or something like that, you want to process that in order. Multiple target systems can be read independently. So PubSub is totally cheap because, again, all you need to do per consumer is you need to keep track of the position. And you need to have enough disk space over here that you can say, okay, if the consumer doesn't pick up the data within a week, we have other problems. Yeah, we just store the data for at least a week. If the consumers don't get it, well, then we have to talk to the engineering department anyways, because then the thing is way too slow. So we can have multiple target systems that can read independently, which has a very, very big impact. This has a huge impact on testing. I'm not sure if you have ever done testing on standard message queuing systems. What you do there is you write a little script that flushes the queue, so you get it empty. Then you write a second script to put test data into the queue. Then you run your thing that processes and that typically reads from the queue and writes into another queue. So then again, you write the script that evaluates the result in the target queue. And if anything goes wrong, you try to find it out and you restart this entire flushing, filling, processing, reading process. You start again. And if multiple developers want to do that, you have to create more queues. Now often the developers forget to change a certain configuration file, then suddenly 2 developers write to the same queue, and then they're wondering why their job doesn't work, and so on and so on and so forth. Now here, that is super easy, because you just test by putting in a topic the test data, and every time you execute, you start from index 0. You just start from the start. If it doesn't go through, you find out which element was it, you fix it, you restart from the beginning. You restart from the beginning, you restart from the beginning. You don't have to dump it out, flush it, refill it, and so on and so forth. So that makes it quite nice. And it also allows you to run multiple versions of processing in parallel. That's something we've done a lot at clients, that for example, if we have a new mobile push capability or something like that, we just run the new version in parallel with a flag so that it doesn't send stuff to Apple or similar, and we just look at the output. And once we're happy with the output, we say, okay, now restart it for real and stop the old job. So, in summary, we have nicer technologies in play nowadays. So we can do on the left our change data capture or batch export. It doesn't matter. For systems, it's often data feeds. For software as a service offerings and different as a service offerings, it's often already built in. For example, AWS, from the colleague from earlier, DynamoDB has a DynamoDB stream where you can get a full change log of everything that is happening. You put it into a scalable distributed log. You have your scalable event processing. Popular ones include Storm, the newer Twitter Heron, Kafka has its own stream processing nowadays. Apache Flink is growing more popular. Or if you're for more analytical things, you can use Apache Spark Streaming. Spark Streaming is a little bit slower. It doesn't do per event processing because it works on micro batches. So you always run it on a batch of data, on a small batch, like 15 minutes. But you can do fancy analytical algorithms. So depending on the use case, you can use what you need. And then in the target, you can just insert with a decent commit size. We once tried to insert each record with a commit into a Teradata, and that blew the system away, so be careful there, logical. Or towards a system, you can do REST calls. And of course, the commercial environment is improving. If you look at the latest offerings from Informatica, at Unity, if you look at the latest offerings from Talent and so on, they are going into that direction. So this Kafka and so on is becoming very, very mainstream and successful. So, just like mobile first or AI first, there's a very, very simple mantra. Go for streaming first when you deal with data. Go for idempotent operations, meaning that when you reprocess something, that you just overwrite it to keep everything nice and simple. If operations knows they can just restart it, and if it runs through, it's fine. It makes life incredibly easy, and you can just stay asleep in the night. Petition to go fast and keep your ordering. And of course, then, while you go, establish some light governance and standards. That's not too much. Of course, you need some naming conventions. Of course, you need some data formats, because Kafka just takes a byte array. You want to standardize that. And of course, your operations. Thanks. Do you have any questions? No? Awesome.
Yeah. Thanks, Dominik. So I have a question, because this sounds kind of almost too good to be true.
No.
So what would be kind of your words of warning, or what are some of the potential pitfalls?
The trickiest thing is actually that this joining in the stream is brutally hard. So if you have to join multiple systems together, you somehow need all the data there, and that doesn't really work within a stream window in a sensible way. So there you need to go for the more advanced frameworks like Flink and so on, where you can really have a point in time. But the thing is, it's improving. It's improving a lot, yeah. And it's getting easier. So the technology is out there. Kafka, we have been using it in production since around 3 years. It was pretty fun back then. It had no security controls, no ACLs, no nothing. Now it has security built in and all that stuff, so it's really becoming serious. And you see that it's successful. Yeah.
Okay.
Thanks.
Any questions from the audience?
Oscar.
Oscar is over there.
So we have run, MQ and ActiveMQ for many years. So we know how to run them, how to monitor, scale, take care of them. But when you look at things like Kafka, it's so new. What are the operational concerns we need to put in place, the operational practices to run that? Scalability, security, monitoring?
Yes. So Kafka from an operations perspective is quite different. What you would typically monitor in your situation is probably queue depth. So you look at how much data is in the queue, because if it's in the queue, it hasn't been consumed. So that's always an indication that something hasn't been processed. In Kafka, you would always have a look at the delta that essentially is the current position of your consumers and the most up-to-date position. So that's essentially the difference. How far are they away from being fully up to date? That's what you would monitor. Apart from that, operating Kafka is significantly easier, because a distributed log can be run in a distributed fashion, and it is a system that from the beginning was built for distribution. You don't need a SAN below it. You just need normal computers, because it has the replication and so on built in. So it's more like Hadoop from an operation perspective. If a machine falls out, it will not be a problem in that regard. And of course, you monitor it like always. Are my nodes up? What we have at my client is that as we have a replication factor of 3, so every piece of data that goes into Kafka is stored at 3 nodes. And we know that the cluster is not in a critical state if one node fails. So if one node fails, we will not wake anyone up in the night. But if a second one fails, that's problematic, because then we get close to the point where we could actually lose data. So then we have to get active. So essentially, we then have green, yellow, red, in contrast to before. But to a certain degree, it's easier, but very different. Yeah. Well done.
Okay.
More?
Yeah. Follow-up
Oscar.
question, I guess.
But then how about from a design perspective? How do I need to design my applications to effectively leverage streaming? How is it changing compared to traditional queuing?
In what regard now?
From a design perspective, an architecture, application architecture perspective.
Well, that depends on what you want to do. If you have streaming at the heart of your system, like for example in the logistics case that we had, we had a lot of systems that anyway generated an event. A parcel comes by, it gets scanned, and I have an event. Then it's pretty natural. I have my topics. So just like you have your queues right now in ActiveMQ or whatever you have your topics, and you punch them in, and then you have the processing from there. It's very different if you adapt an existing application into that way. So then you have to check in your transactions, where are the points where I want to send out the message, and then generate it from there. But it then becomes a very nice pattern, because essentially writing to Kafka is something that rarely fails, because it's always this question around coupling. If you are coupling to many systems, then of course you can go down easier. If you just write to Kafka, which has a very good high availability story and doesn't do a lot of processing, it just takes your byte array, is most probably it will succeed. So you can depend on it, and then you can do the other stuff decoupled. But of course, the monitoring of the consuming pieces is again the second part, namely you have to monitor Storm, or you have to monitor Spark Streaming or something like that. So I would really recommend to do a conscious decision which frameworks you use. I have seen clients where essentially the developers chose themselves. So some people were using Spring Batch, the other ones were using Storm, and the next group was using Flink because it's cool, but no one had a clue how to monitor those 3 things. But that's not surprising to a certain degree.
All right. So thank you, Dominik. That was interesting.